Okay. So morning, everyone. So today I am going to be giving you guys an introduction to Neuralink. The topics I'm going to be covering is what is Neuralink, the potential applications of Neuralink, the implants, the surgical robots, the surgical procedure, and the role of the surgical robots in the procedure. So Neuralink is a neurotechnology company founded by Elon Musk with the goal of developing implantable brain-machine interfaces. The company's objective is to create advanced technologies that establish a direct link between the human brain and computers, allowing for bidirectional communication. The concept behind Neuralink is to enable humans to merge with AI systems, potentially unlocking new capabilities and addressing neurological disorders. Neuralink's ultimate vision involves the development of implantable devices that can interface with the brain's neurons to transmit and receive signals. These devices could potentially assist in treating neurological conditions, such as giving people with quadriplegia the ability to control their computers and mobile devices with their thoughts, restoring capabilities such as vision and motor functions. So now I'm going to move on to the potential applications of Neuralink. All right. So in terms of future application, one thing the Neuralink team is heavily focused on is vision. So the visual cortex is relatively well understood, and Neuralink's equipment is capable of inserting electrodes deep enough not only to read what's happening in a sighted individual's visual cortex and directly stimulates the cortex. Neuralink's equipment is capable of inserting electrodes deep enough not only to read what's happening in a sighted individual's visual cortex, but also to send information directly to the cortex. In theory, this could eventually mean that the device could take a signal from a camera and directly stimulate the cortex, such that somebody that was born completely blind could gain a low resolution sense of vision, which could improve over time as the technology improves. So the Neuralink team has made a certain degree of progress in this area. They've implanted monkeys to move their gaze in the direction of flashing lights in exchange for banana smoothies. And then they started replacing the real flashing lights with brain signals sent through the Neuralink implants. And sure enough, the monkeys glance over to the exact spots targeted by the brain implant, as if there's a real flashing light there. So this was Neuralink's first step, I guess, at creating what will eventually become a display that they hope is what will allow to see. This was Neuralink's first display. This was Neuralink's first step towards displaying what they hope will eventually allow blind people to see. So the next target is even more ambitious, which is restoring motor function after paralysis. Neuralink hopes to use its implants to read motor commands from the brain and then reroute them around serious spinal cord injuries into lower motor neurons that could get the messages right through to the muscles. Again, the team has made some progress towards this goal, implanting the device in both the brain and spinal cord of pigs. That the team began to decode which patterns of brain activity signaled the motor intentions that resulted in which patterns of electrical activity in the lower spinal cord. The researchers were able to identify the patterns responsible for certain movements, and then they were able to replicate some of those movements as well, directly stimulating the spinal cords to cause, for example, muscle contractions that will lift the pig's leg up. The team isn't just targeting motor signals. They also want to restore sensation by rerouting messages in the opposite direction back to the brain. So this would require additional implants in the sensory cortex. Putting these two loops together, they have the motor intention decoded from the brain used to stimulate the spinal cord, causing movement, and then the sensory consequences of those actions being recorded in the spinal cord to stimulate the brain, causing perception. And lastly, another application of Neuralink is the enhancement of human cognitive abilities. By connecting the human brain with a computer, individuals could potentially improve their memory learning. They could potentially improve their memory, learning, and problem-solving abilities. So the next thing is the implant. So the implant is cosmetically invisible and designed to let you control a computer or a mobile device anywhere you go. The implant is hermetically sealed in a biocompatible enclosure that withstands physiological conditions several times harsher than those in the human body. The implant is powered by a small battery charged wirelessly from the outside via a compact inductive charger that enables easy use from anywhere. The implant uses advanced custom low power chips and electronics that processes neural signals, transmitting them wirelessly to the Neuralink application, which then decodes the data into actions and intents. The implant records neural activity with 1,024 electrodes distributed across 64 threads. It allows 1,024 channels of two-way communication between the brain and the chip through 64 tiny flexible needle probes inserted into the brain tissue at precise points. These highly flexible, ultra-thin threads are key to minimize damage during implantation and beyond. And also the implants will be both removable and upgradable. So next up is the surgical robot. So the threads of the implants are so fine that they can't be inserted by the human hand, which is why the team introduced the surgical robot it uses to implant the device. The surgical robot has been designed to reliably and effectively insert these threads exactly where they need them to be. The base structure and motion of the robots provide the structural platform for the robots and for the primary 3-axis linear motion used to position the robot head and the needle. The robot head contains the optics and the sensors of 5 camera systems and the optics for an optical coherent tomography system. And lastly, the needle, which is thinner than a human hair, grasps, inserts, and releases threads. Next up is the surgical procedure. So the first step of the surgical procedure involves the surgeon making a small incision in the scalp, exposing the skull. Next, a small hole is drilled into the skull through which the robots will insert the electrodes into the brain. The robot is controlled by a trained professional who uses high resolution imaging to guide the robot and ensure that the electrodes are inserted at the correct depth and location within the brain. Once the electrodes have been inserted, they are connected to a small device located behind the ear. This device is responsible for transmitting signals between the electrodes and an external device such as a computer or a smartphone. So the role of the surgical robots in the surgical procedure. The Neuralink robot plays a crucial role in the surgical procedure. It's designed to minimize the risk of damage to surrounding tissue during the implantation process. The robot utilizes advanced imaging technology to create a 3D map of the brain, allowing the surgeon to accurately place the electrodes without damaging any critical areas of the brain. Additionally, the robot is able to adjust its position in real time, ensuring that electrodes are inserted in the correct depth and angle. This is important because the brain is a complex organ and different areas of the brain require different levels of stimulation. So by accurately placing the electrodes, the Neuralink device is able to provide the precise stimulation desired to the desired area of the brain. So in conclusion, Neuralink technology, which allows for real-time communication between the human brain and a computer, has potential applications in the treatment of neurological disorders, enhancing cognitive abilities, and human-machine collaboration. As the technology continues to develop, we can expect to see even more exciting applications in the field of neuroscience. Thank you.